So in previous videos, you've seen where we've taken the slope of a graph to figure out, for example, the velocity from the position time graph, or to figure out the acceleration from the velocity time graph. In front of you here, you can see a graph of velocity versus time. And if I wanted to find the acceleration of the object from 0 seconds to 4 seconds, I could take the slope and say that the acceleration of this object is rise over run, 4 over 2. So the acceleration is 2 meters per second. The y value over seconds, 2 meters per second, that's acceleration. And so we take the slope and we're able to find that value. We could then go on and graph this from a velocity time graph to an acceleration time graph. But in this case, we want to work our way backwards. So let's say that we have a velocity time graph. I want to figure out something about the displacement. The opposite of taking slope is taking the area. The opposite of addition is subtraction. The opposite of multiplication is division. The opposite of slope is area. And so if I have this velocity time graph and I want to figure out displacement, I could do that by taking the area under the curve. And what I mean by under the curve is we take this graph here, and the area of the shape that is pinned in by the x-axis is the net displacement for the object during the 4-second interval. Now, normally we don't solve this as one shape. We break it down into a series of shapes, and then we can calculate using the idea that area is length times width, and that area is 1/2 base times height, and we can then use that information to figure out the net displacement. So in the first 2 seconds here, we have a triangle that's has a base of 2, so 1/2 times 2 times a height of 4. That gives us an area of 4. The area here would be 4. The next second, from 2 to 3 seconds, we have a rectangle that has an area of 1 times 4, or 4 again. For the next second, that shape is more of trapezoidal, that we have a diagonal line and a vertical line. We get a trapezoid out of this. And so we break that into the rectangle and the triangle, and we add it together. So in that case, we have a triangle that's 1/2 1 second wide by 2 seconds high. And then we have to add to that the rectangle that's on the bottom, which again is 1 second wide by 2 seconds high. And so we get, when we solve this, 3. And so the area of this whole thing is 3. So the net displacement of the object over the 4 seconds is going to be 4 plus 3, or 11 meters. Now, to understand how that works, I'm going to just look at this first 2-second period. We realize here that the velocity is changing at a constant rate. And when the velocity is changing at a constant rate, a nice linear slope, the middle value is going to be the average velocity. So for half the time you're going less than 2 meters a second, and for half the time you're going more than 2 meters a second. So the average velocity here, and this only works when we have an acceleration that is constant, which means that the slope of the line is not changing. In that case, the average velocity is going to be equal to the final velocity. Final velocity is 4, plus the initial velocity of 0, divided by the total time, which is 2 seconds. So the average velocity here is 2. That only works again when acceleration is constant. And so what we are going to see in this particular portion of the triangle is that the average velocity being 2, happening for 2 seconds. So displacement is equal to velocity times time, average velocity times time. So x is equal to 2 times 2, which is 4, which means the displacement's 4. That's the same as the area. And so we have been able to mathematically solve for that displacement in that particular portion of this problem, 2 different ways, getting the same exact answer. Take the area under the curve or figure out the average velocity and then multiply that by time using our displacement is equal to velocity times time equation. If you have any questions, let me know. Watch the next video in the series where we will do this to graph a position time graph from a velocity time graph.